Hi everyone, welcome back to our channel. Today we are going to analyze how an alternating current through an series RLC circuit is going to develop an impedance triangle. Okay, so let us try to see here. We are going to have an resistor. So this is a resistor R ohms, and we are going to have an inductor. This inductor value is plus JXL ohms, and it is excited with an AC supply of V volts. Okay, so now the whenever the current enters, I'm labeling this current as I of t. This is entering is positive, leaving is negative. Entering is positive, leaving is negative. The voltage developed across the resistor is VR. The voltage developed across the inductor is VL. Okay. Now, when you apply the KVL, so actually it is an AC supply. We should not mark terminal. Why I marked the terminals is to do the analysis easier. Okay, this instantaneous voltage is represented as V maximum sinusoidal of omega t minus 0 degrees. Okay, so this current we want to write down. Current I of t we can write down as I maximum sine of omega t minus phi. Okay, this is how to write down. So now when to link all these voltages and currents, we are going to apply KVL inside the loop. So when you apply the KVL, the leaving voltage is plus V, and leaving voltage terminal is minus VR, and the leaving terminal is minus VL is equal to 0. Therefore, applied voltage V is equal to VR plus VL. So these are like a vector addition. Okay. So now let's try to draw the vector diagram for this. And we can write down V is equal to, when they are an vectorially added, we can write down VR square plus VL square. Okay, so now when you're trying to draw the phasor diagram, let's try to understand how the phasor diagram is. Okay. So the phasor diagram we are going to draw in this fashion. Okay, so while drawing the phasor diagram, I'm taking the voltage as an reference, VL at an angle of 0 as an reference. So the current across the inductor is equal to, current I is equal to VL by R. R is nothing but plus J XL ohms. That is nothing but VL divided by XL. This 90 will go to the numerator, and I can write it as a minus 90 degrees. Okay. So here, whenever it is minus 90, for example, if you take this as a reference, when it travel in counter clockwise direction, then we should consider it as positive theta. Okay, whenever travels in clockwise direction, we should consider it as minus theta. This is what the reference phasor notation. Okay, so here you are getting an angle of minus 90. Therefore you are going to get the current where it is nothing but the current across the inductor, and the magnitude of this current is VL divided by XL with an angle of minus 90. Okay, so the angle traveled here is how much? Minus 90. Okay, so if you take this as a reference, so you have uh, bus 1, bus 2, bus 3. Okay, so whenever this first bus is traveling like this, and this is the second bus, and this is the third bus, this second bus I'm taking as an reference. If the first bus is running very fast, then I can say that this is the capacitive current. I can say that IC lead V and V lags by some phi. So for example, second bus, this is the first bus is moving very fastly, and this is the reference bus, and third bus is coming very slowly. So how to write down the current here is IL lags voltage V by 5, or IL lags and V leads by 90 degrees or 5 degrees. Okay, so here that's how to understand. We have to take one as a reference. Here, what is lagging? Current lags. I mean, the current across the inductor lags the voltage VL, and VL leads by 90 degrees. This is how to understand current lags a voltage in an RL series circuit. Okay, so this VL or RL you can take whatever you want to. So now let us try to draw the voltage triangle, and from voltage triangle we are going to draw the impedance triangle, and from impedance triangle we are going to draw the power triangle. It's very important. So how to draw all these triangle? So initially you can see here. So we are going to construct V is equal to VR plus VL. Okay, so first I'm drawing voltage across the resistor. This is nothing but voltage across the resistor. We are at an angle 0, and now we need to draw the value of VL. VL is equal to I into plus J XL. So this I can write down it as I into XL at an angle of 90 degrees. So how to draw this 90 degrees is, so we need to uh, draw it in an upper direction. So this is nothing but at an angle of 90. So when you're drawing in this direction, what is the angle made in that counterclockwise direction is plus 90. Okay, so we are magnitude, and since it is scalar, the direction is like this. This is VC magnitude I into XL, and the direction is upward direction. If you add these two, then we are going to get the vector. Okay, so then we are going to get the value of V. Okay, therefore V is equal to vector addition of V R as well as VL, then we are going to get the value of V. Okay, next one, how to draw the impedance triangle. So this I'm going to draw in one more fashion by taking phi here. Okay, so when I find cos phi, so what is cos phi of this? Cos phi, as well as I'm going to find sin phi from this triangle. So sin phi is equal to, sin phi means opposite. What is the opposite value? VL divided by hypotenuse. Hypotenuse value is V. What is cos phi? So to this 90 degree, what is there? VR. VR divided by V. So VR I can write down it as V cos phi. The same triangle is replaced like this, and horizontal line with the value of VR is equal to V cos phi, where this is called horizontal component of voltage. This is called horizontal component of voltage. And now VL value is V sin phi. So here we are going to get VL is equal to V sin phi. This is called as this line is vertical. This is called as vertical component of voltage. So vertical component of voltage. So resultant you are going to get, which is nothing but V. So from this voltage triangle, we need to draw the impedance triangle. Okay. So VR I can write on it as I into R. VL I can write on it as plus I into, so I into plus J XL ohms. Okay. So from here it is here how to draw the impedance triangle. So this triangle you have to divide by 1 by I. Therefore, what we are going to get here is, so Z is equal to V into 1 by I, we are going to get Z. So divide this all the sides by I, then you are going to get this triangle. When you divide IR by I, then you are going to get only resistance. This is nothing but the X horizontal component is resistance. So IJXL, when you divide, then you are going to get the one more component, which is nothing but JXL. Okay, and this resultant is called impedance. It's nothing but Z. So here you are going to have phi. So the impedance Z we can write on it as R plus JXL. How to, this is like an rectangular form. We can write down in polar form, which is nothing but root of R square plus XL square is the magnitude, with an phase angle of phi is equal to tan inverse of imaginary part. Imaginary part is XL by R. This is what the impedance offered in a series RL circuit. So this is the voltage triangle, this is the impedance triangle, and multiply this voltage triangle with current, then you are going to get concept of power triangle. So therefore, so voltage into current, I can write down this as VI cos phi is the horizontal component, where this power is called as active power, where the active power is represented with the symbol P, and this power is also called real power. Okay, and this vertical component V sin phi is once again multiplied with this, and then we are going to get this value. So it is nothing but voltage into current. Therefore we are going to get this value as a VI sin phi, where this we are represented as a power which is called reactive power, where Q is called reactive power. Okay, and the vector addition of these two, which is called as S, where S is called as apparent power. This is very 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 important to understand. This is called apparent power. Okay, so here the phase angle made by this is called power factor. So active power, the symbol is P, and it is called active power or reactive power. Why it is called real power means S is equal to, we can write down it as a P plus JQ. We can write down it as P plus JQ. So JQ means this is nothing but direct, it will come in 90 degrees. So this is available in real side or real number, that's why it is called real power, and this Q is there in imaginary part, that's why it is called reactive power, or this power is called imaginary power, and the resultant power is called apparent power. The units of active power are watts, or in kilowatts we can write down. The units of reactive power we can write down it as a volt ampere reactive. Okay, so we can write down the units as volt ampere reactive, or we can write down it as a kVAR. The units of apparent power is volt ampere, or you can write down it as a kVA. That is how to obtain a voltage triangle. Divide the voltage triangle, then you'll get impedance triangle, and the voltage triangle you multiply with the current, then you're going to get the power triangle. This is how to obtain a power triangle for the given problem. Okay, so now the remaining part, how to calculate the power factor, the power, we'll try to do in the next video. Thank you for watching. We'll meet in the another video.